Good morning. Last week we gave a bit of a broad overview of properties of atoms, and we've seen how those properties make atoms engage into interactions and form molecules. We talked about molecular structure, and we talked about representations of those structures in terms of structural formulas and condensed formulas. Today we'll take a step back and we will see in a bit more detail how exactly do atoms combine to form molecules. And to do that, we will review atomic orbitals first, and then we will see how they combine to form molecular orbitals. An important property of electrons, which was established in the 1920s, is that they are both particles, but they're also waves. And when you think about waves, you might think about waves that you see in Galveston, for example, which are called the traveling waves, as since they move from the sea towards us standing on the shore. But electrons are really represent a different kind of waves called standing waves. And these waves are more closely analogous to, for example, oscillations of a guitar string, which, if we know how guitar string looks like, is fixed in 2 points at its ends. And hence once we set this to vibrate, those two ends do not move, but the center of the string moves and has a positive amplitude here. And then the next moment it has the negative amplitude, as shown here. Okay? In a molecular world, this corresponds to a 1s orbital, and as we've seen last week, 1s orbital has the following dependence of electron density versus distance from the nucleus. And in three-dimensional space, 1s orbitals, as are all the other s orbitals, are represented by these spheres, which are therefore non-directional, since they're the same in all directions. At this point, signs plus and minus have very little physical significance. It is really the square of this amplitude, also known as psi squared, which tells us what's the likelihood of finding an electron at any given spot. However, I mentioned that at this point, these signs have no meaning. We'll see very soon that when we talk about molecular orbitals, these signs become very meaningful because they need to match in order to form a productive overlap needed for molecular bonding. Now, these have been the s orbitals, but we can also imagine another analogy with a guitar string, where we have a guitar string which is fixed at both ends, but it's also fixed in the middle, as if we clipped it there with our finger. Now when we set this to vibrate, the first half will move in a positive direction, whereas the second half will move in a negative direction. And the 3 spots where the guitar string is fixed will not move at all. In the very next moment, the first half will now have a negative sign, the second half will have a positive sign. And this sort of a vibration corresponds to what we've seen being called a pi orbital, which has the following dependence of electron density on distance of the nucleus. And in 3 dimensions, this sort of looks like a dumbbell. In this case, this will be a pi x orbital, because it's aligned along x-axis. This point here is a node, because the wave function density here is 0. And in fact, this whole plane represents a nodal plane, because at that point, electron density is 0. Again, all of these points are nodes as well, because the electron density function is 0 there. Now, the concept that creates molecular orbitals from atomic orbitals is known as the linear combination of atomic orbitals. It's also known by its acronym LCAO. For 2 orbitals to interact, they have to be the same symmetry, and they also have to be similarly positioned in terms of energy. And we'll see in the next topic how atomic orbitals combine to form molecular orbitals.